In this video, I want to talk about the final step in our examination of languages in the Chomsky hierarchy. So far, we have not seen any languages past or outside of the Turing Decidable set. But there are such languages. It's just a little difficult to describe them. So that's what this this worksheet and this video is going to attempt to do. So let's get started. First, we have to talk about what is meant by a countable infinite set and an uncountable infinite set. There are different sizes of infinity, which is kind of a strange thing to think about, but it's true. And if you can prove, which we intend to do, that there are more, for example, languages than there are Turing machines, then there have to be languages outside the hierarchy. So, and that's where we're going. We want to make that claim that there have to be languages outside the hierarchy. So what we want to show is that the set of all Turing machines is a countable set, but the set of all languages is uncountable. That means it's bigger. There are more languages than there are Turing machines. But let's take that a step at a time now. Let's back up just a little bit and let me define what I mean by a countable set. First of all, any finite set is definitely countable because you can count the things in it. And you can say, oh, there are 42 of those things. So really we're concentrating on infinite sets. If you say that an infinite set is countable, you don't mean that there is some certain cardinality number like 42 that is how many things there are in the set. That's not what we mean. What we do mean is that you can assign a cardinal number, a counting number, to each element of the set so that every element has its place in the list. In other words, you can put the contents of this set in some sort of order so that every single one of the infinitely many things in this set has its own place in the line. Everybody is in there and nobody is left out. If you can do that, if you can order the elements of the set in some way that no element is omitted, then you say the set is countable. So which sets are countable? The integers, all of the integers, the negative ones and the positive ones, can be put into an ordering. Now you can't just start at 0 and say, oh, we'll list all the positive ones and then we'll come back and list all the negative ones, because you will never get finished listing the positive ones. So that is not an appropriate listing technique. What is to bounce back and forth. Pick a starting point. Pick 0. That makes sense. Pick 0 and then go up 1 and then back 2 and then up. So you go from 0. I get lost when I can't write with this presentation here, and so I get kind of lost. But let me see if I've got, okay, here's a mouse. I can point. Start at 0. Go up 1, and then on the number line you'd be going back 2 to -1, but -1 comes next. And then you'd be going doink, 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 and up 3 to 2, and then back 4, and up 5, and back 6, and so forth. And you'd get this ordering here, where you're bouncing back and forth around 0, positive, negative, getting farther and farther from 0 as you go. Now you see these little numbers here? These are the numbers that I'm assigning, that I am mapping to these numbers. So this is the first one in the list, this is the second one in the list, and the third one in the list. Another way of saying that a set is countable is by saying that there exists a one-to-one mapping between these counting numbers and the elements of the set. And I suppose I should have started here at 0, since most computer science people do, but whatever. Here's another set that's countable. It's the set of all rational numbers. Now remember, a rational number is a number that can be written as a fraction, as a numerator over a denominator. And that is an infinite set, of course, and it's kind of surprising that that set is countable. How would you go about listing all the fractions? Well, you certainly couldn't say, let's do all of the ones that have a 1 in the numerator first, and then we'll do all the ones that have a 2 in the numerator, and so forth, because you will never finish the ones that have a 1 in the numerator, and you'll never get around to doing the ones that have a 2. But you can do it this way. This gives you a starting point. You make a table. These are numerators. These are denominators, and inside here are all the fractions. So here we have 1 over 1, that's this one, and then 1 over 2, and 1 over 3, and so forth. So we just make this big old infinite table. It has infinitely many rows and infinitely many columns, but it has this upper left corner. It's kind of like a Turing machine. No, I shouldn't really say this because it's not really like a Turing machine, but you know how a Turing machine's tape might have a starting point and be infinite only in one direction? Well, this table has a starting point right here, and it's infinite in these other two directions. So what you can do is you start here at this starting point, and then you weave your way along these diagonals back and forth, and you will eventually get to everything in the whole table. So that gives you a way to put the things in an order. What else is countable? Strings made out of A's and B's is a countable set. We've seen how to list these guys. You list first by length. So here's a string of length 0. Here are two strings of length 1. And when you have more than one string of a certain length, you put them in alphabetical order. So here are 4 strings of length 2, and you notice they are in alphabetical order. This ordering technique is called lexicographic ordering, and we've talked about this before. Now, if you can list the set of all strings made out of A's and B's lexicographically, you can certainly list subsets of that big set lexicographically, and here are some. Here's double word, just the beginning of it, and you see these strings are listed lexicographically, first by length, and then within a set that's tied in length, you list alphabetically. Here are palindromes. Here are strings that have equal A's and B's, and they're all countable. Now this is kind of odd. The set of all Turing machines is a countable set. Now how in the world do we get that? Well, that goes back to the idea that a Turing machine can be encoded as a string. Remember, we had a little scheme that we cooked up to turn our simple little Turing machines that only required 4 characters into strings, but you could enlarge our encoding scheme and turn any Turing machine into a string. And since you've turned it into a string and the set of all strings is countable, then the set of all Turing machines is also countable. You could do the same thing with programs. Think about the set of all possible Java programs. Kind of mind-boggling, isn't it? Is that set countable? Could you put all possible Java programs into a list? Well, you could. When you think about it, you could just treat it like a meaningless string and impose an ordering on all the possible characters that you can put into a Java program. The ASCII code would do as your ordering scheme, as your alphabet. I mean, we have an order for the letters and we have an order for the digits, but what order are the punctuation marks in? You'd have to impose some sort of ordering on all the various characters that can be put into a Java program. But once you had done that, then you can just think of a Java program syntactically and not semantically. So it doesn't have any meaning. It's just a string, a big old long string sometimes, a string that might spread over many files even, but it is still a string, and you could put all those big old strings into alphabetical order. So the set of all Java programs or all C++ programs is a countable set. But are all infinite sets countable? The answer to that is no. This is not on the worksheet that goes with this lesson, but the real numbers are not countable. You can think of all of the real numbers, all the various spots along the real number line, which is a continuous line now that goes forever in both directions. Any number on there is a real number. And when you think about all of them, that's kind of mind-boggling. You know, because no matter which two you pick, there's at least, well, there's infinitely many in between them. No matter how close you get, two numbers on that number line, if the two numbers are different, then there's infinitely many numbers between them. So you can look at just a little range on the real number line, the real numbers between 0 and 1, and you can prove that you can't put the numbers between there in any kind of reasonable order. There is no ordering scheme for the real numbers, so that set is not countable. And here's another one. The power set of an infinite set is not going to be countable. So if you take something that is countable, like say the integers, and then you consider the power set of the set of integers, which is the set of all subsets of integers, there are more subsets of integers than there are integers. And if the set of integers is countable, then the set of all subsets of integers is not going to be countable because there's more of those things. So any power set of an infinite set is not going to be countable. This talks about the set of natural numbers. Natural numbers are 0, 1 to the non-negative integers. That's what we call natural numbers. They're also called counting numbers. And you can prove that the power set of these numbers is not countable with kind of an interesting proof technique that's important to understand because it shows up in lots of places. It's a proof by contradiction, and you actually make a big table as part of the proof. So let's go through this. Let's assume that the set is countable. This is the power set of the set of natural numbers. Assume it is countable, and by that assumption you say, well, then there has to be a way to list them all. Now, we don't want to get into the details of a specific listing technique. We just say there has to be a way to list them if our assumption is correct. So let's just give variable names to all the subsets. We'll call them S0, S1, S2, and so forth, and we'll put them in a list. Here's a table that has each subset written on a different row. These are subsets of natural numbers. Now the natural numbers themselves are written as column headings. And they keep going forever and ever and ever out this way. So 6, 7, 8, 9, they're all written out through there. 1 million, 2 million, 3 billion, 5 trillion, so forth. All the ones are out through there. And the power set of that set's an infinite set, so there are infinitely many rows too. But we've assumed that every single subset will have its place in this table. Now we set about proving that that can't be true. Now what's inside here in the contents of the table? Well, there's trues and falses that we represent with ones and zeros. So, woo, what did I do? Hold on. I did something goofy. As usual, huh? Here we go. Okay, so inside here we put a 0 if the natural number 0 is not in that subset. 1 is not in that subset, so we put false right there. 2 is not, but 3 is. And I just randomly picked 1s and 0s to put inside this table. This is meaningless. I just picked some random numbers, you know, because I don't know what what this actual order is here. I've just assumed that it's orderable and there's an order. So the table is kind of a Boolean array. Now, how do we show that the set is not countable using this Boolean array? Well, by our assumption that it is countable, what we've said is that every single subset is in that order somewhere if the set's countable. So what we have to do is find a set that we can argue cannot be in that table anywhere. Therefore, our assumption has to be wrong. We've assumed that every set's in there somewhere. If we can find a set that's not in there, then our assumption is wrong. So we show how to create a row that cannot be anywhere in the table. Now, how do we do that? Well, we look at the diagonal. We look at the cells along the diagonal. Let's go back up to this table. These are the cells that I'm talking about. You look at these cells. And what we want to do is make a new row that will be different from every row in this table. And we do that simply by flipping the value on the diagonal. So if the first row, or let's say the 0th row, has a 0 in this place, then in our new row that we make, we're going to put a 1 there. And if this cell, which is cell S1 and 1, if that has a 1 in it, then we're going to put a 0 in our new row. We're just going to put the opposite of each of the diagonal cells into our new row. So for the 0 column of the new row, we look at 0, 0 in the table, and we take its opposite, and we put that in our new row. For 1, we look at 1, 1, and we take its opposite, and we put that in our new row. For the 2 column, we look at 2, 2, and we take its opposite, and we put that in our new row. And we do this forever. We have to, because this table is infinite in both directions. And so what we're doing is creating a row that will be different from every single row of the table in at least one cell, because we force it to be different from the cell that's on the diagonal of every row. And since we've discovered how to turn up a row that can't be in the table, then we've shown that the table's not complete. And therefore our assumption that the table is complete is wrong. Now, we just fiddled around with the power set of the set of natural numbers. What is the power set of the set of all strings over AB? The power set of the set of strings is the set of languages, because think about it, a set of strings is a language. And if you think about the set of all possible sets of strings, that is the set of all languages. And that is the power set of the set of strings. And we've shown by that previous argument that a power set of an infinite set is not countable. We could do that same exact diagonalization thing for the set of languages. And here's what the table would look like. Listed down this way would be all the different languages, and over across here would be all the different strings, and you just put 1s and 0s in the table depending on whether that string's in that language. And then you can use that same technique of flipping whatever's on the diagonal, making a new row that can't be anywhere in the table, and therefore you prove that the set of all languages is not a countable set. So now down to the important idea. Are there more languages than there are Turing machines? Yes, there are more languages than there are Turing machines. That's because we've shown that the set of Turing machines is countable. You can represent a Turing machine as a string. The strings can be listed. So that set is countable. but the set of languages, which is the power set of the set of strings, is uncountable. So there are more languages than there are Turing machines. And thus, there must be languages that are outside the Chomsky hierarchy, because the Chomsky hierarchy contains only the languages that can be recognized by Turing machines. Each Turing machine has a specific language that it recognizes. So only the languages that are recognizable by Turing machines are in there. And since there are more languages than Turing machines, there have to be some that are not in there. Let's find one. Here's a weird description of a language. And this is the one that we're going to find that's outside the hierarchy. It's the language. Now, our alphabet is changing here to just make things as simple as possible. We're working only with the alphabet that contains A's. That's it, only A's. So this language is the set of all strings made only of A's, where the length of the string now is this I. And the string A to the I is not accepted by the ith Turing machine in the list of all Turing machines that accept strings made only of A's. All right, so let me say this again. We've restricted our alphabet to just A. Imagine all the possible Turing machines that you could cook up that work only with strings made of A's. So it could be strings of even length made only of A's, strings of length that's a multiple of 7, strings of length that's prime, of length that's a power of 14, I don't know, just something that you can describe that only deals with the letter A. Have at least 49 A's in them, all those kind of things. So imagine all of the many Turing machines that work only with strings made out of A's. Turn all those Turing machines into strings by some encoding technique and make a list of them. Put them in alphabetical order after you get them turned into strings of, turn your Turing machines into A's and B's, and then make an ordering of all your Turing machines. Now, there will be a first one in that list, or a 0th one. There will be a number 1, there will be a number 2 in the list, a number 3, and so forth. So now imagine that each of those Turing machines that's inside that list of Turing machines, you've named it. You've named it by its number, starting with 0. Your machine 0, your machine 1, your machine 2, and so forth. Now those same numbers by which you've named the machine can be lengths of strings. You can have a string of A's of length 0, that's lambda. You can have a string of A's of length 1, a string of A's of length 2. So what we're doing is matching up the string of a particular length with the Turing machine whose name is that number. And we are saying that our language consists of all the strings that do not get accepted by the Turing machine whose name matches that string's length. You get it? All right, well, let's take it a little bit more slowly. So we know that Turing machines can be listed by their encoded strings. Think of all the Turing machines that work with just A's. Make a list of them. And put those Turing machines into a table like we've been looking at, where the rows of the table are these Turing machines. So it looks kind of like this. This is the row that belongs to Turing machine 0. And I've put L parenthesis around Turing machine 0 to represent the language that gets accepted by Turing machine 0. This is the language that gets accepted by Turing machine 1. So I took my list of Turing machines and I made a table of the languages that each of those Turing machines accepts. And then I put across the top of the table all the possible strings that you can make out of A's. String of length 0, in other words, lambda. This is A, this is AA, AAA, and so forth. Now, I want to look at the contents of the cells on the diagonal here, because these are the cells that are important to me, because my language contains all the strings that are not accepted by the machine whose name matches the length of the string. So this string, if this is the table that I make, then this string is not in my language, but this string is, because there's a 0 there. It's not accepted by the machine whose name matches its length. This one is, this one is, this one is, and this one is. Now remember, I'm just making up things here to put in this table, but it doesn't so much matter exactly where the 1s and the 0s are in my example. What is important is the concept that I am getting at. So let's name two languages now based on that table. Let's call the language that contains all the strings that have 1s on the diagonal, let's call that L. And the language of strings that have 0s on the diagonal, call that L prime. So between them, L and L prime contain all the strings in the whole table. Strings made out of just A's. Either a string is in L or it's in L prime, because either it has a 0 on the diagonal, which puts it in L prime, or it has a 1 on the diagonal. Those two languages are complementary. And we're going to show that this language of strings that have 0s on the diagonal is outside the hierarchy. And then we'll talk about where's the other one. How are we going to prove that that language of strings that have 0s on the diagonal, the one we're calling L prime, how are we going to prove that that language is not Turing acceptable, that it is outside the hierarchy? It's going to be a proof by contradiction, as so many of our proofs are. We're going to assume that it is inside the hierarchy, that it is Turing acceptable. So then it must have a row in that table, because that table contained a row for every Turing machine. So if our language is Turing acceptable, that means it has a Turing machine. And that table contained all the Turing machines. So it has to be in there somewhere. But how could that be? How could there be a row that matches up with our language L prime? That machine that we're talking about, if L prime is Turing acceptable, then it has a Turing machine, and that machine has to accept the strings that are in L prime. And L prime contains the strings that have 0s on the diagonal. So could the row that goes with the machine for L prime be one of the rows that has a 0 on the diagonal? No, because L prime contains the strings that have 0s on their diagonals, and so the row that goes with L prime would have to have a 1 for the string that's on the diagonal, because that string gets accepted because it had a 0 on the diagonal. You see how confusing this can get? Could the row for the machine that goes with L prime be a row that has a 1 on its diagonal? No, because the language L prime doesn't contain any strings that have 1s on the diagonal, so its row would have to have a 0 for that string. So it can't be a row that has a 0 on the diagonal, and it can't be a row that has a 1 on the diagonal. Therefore, it can't exist. It is not anywhere in that table. Thus, L prime is not Turing acceptable. Now, what about the other one? What about the complement of L prime, which is L, which is the language of all the strings that have 1s on the diagonal? Is it in the hierarchy? Actually, yes, it is. Here's a Turing machine whose job it is to accept strings that have ones on the diagonal. Here's what it would have to do. You give it a string made of A's, and it has to count the number of A's in that string. So let's say the number is 7. It's A to the 7th. What it has to do next is start generating all the Turing machines and stop when it gets up to number 7. When it finds the 7th Turing machine, because it was given a string of length 7, then it has to run that Turing machine on that string. And if that Turing machine accepts the string, that means the string would have a 1 on the diagonal, and our machine would need to accept that string. But otherwise, it would need to reject that string. Now, there's a slight problem here that some of you are going to pick up on. The only way to determine whether or not string A to the I is accepted by Turing machine I is to run it. Run the right Turing machine, the ith Turing machine, on the ith string. Just run it. And if the Turing machine accepts, then you say, yeah, that's one of the strings that has a 1 on its diagonal, so that belongs to my language L. But remember that weird, quirky thing that Turing machines can do? What if you never get an answer when you run Turing machine I on string A to the I? What if the sucker goes into an infinite loop? Which is possible with Turing machines. Then you never get an answer. So there's kind of a flaw here, a subtle flaw. And we begin to wonder, maybe this language L is Turing acceptable. I mean, if the machine accepts the string, then clearly you've got your answer and you know that that string is in your language. But what if the machine just keeps running and running and running and running? Maybe it's just taking a really long time, but maybe not. Maybe it's in an infinite loop. You'll never know. That's kind of a problem. So what we need is a clear argument that either L is Turing decidable or it's not. And we think it's not because of this subtle problem with the infinite loop business. But here's a better way to argue that it is not Turing decidable. We can show that the set of Turing decidable languages is closed under every one of our set operations. It's closed under union, concatenation, intersection, Kleene star, and complement. It's closed under everything, just like the set of regular languages was. And since we've shown that L prime was not even Turing acceptable, then its complement L can't be Turing decidable, because if it was, so would L prime be Turing decidable because the set's closed. So let's go back one slide. Here's a little bit of a proof that the set is closed under complement. If you have a language that is Turing decidable, then its Turing machine always gives a definitive answer. It always goes to the halt state and says yes, or it crashes and says no. Well, you can flip things around so that you give it a reject state instead of letting it just crash, and you give it a halt state, and then you swap those two things, and so you build a machine that says no every time the other one said yes, and says yes every time the other one said no, and you have a clear decision procedure for the complementary language. And that's an argument that the set is closed under complement. And that leads us to this notion that the language L is Turing acceptable, but it is not Turing decidable. So now we have a language in every one of the concentric circles of our Chomsky hierarchy, and we even have a language that is outside the entire hierarchy. So what this really means is that there are languages that you can't recognize with an algorithm. Remember, we equate Turing machines by Turing's thesis. We say that if a problem is solvable algorithmically, then it can be solved by a Turing machine. So there are languages that can't be recognized by any Turing machine. And so what that really means is that there are problems that cannot be solved algorithmically. Not every problem is solvable. This is getting into the whole realm of computability. And in advanced theory, we talk much more about this. Actually, Alice McRae talks much more about this because she's the one that typically teaches that course. And you talk about whether problems are solvable or are not solvable. And how important is that? I mean, if you attempt to solve a problem that's not solvable, then you're just going to be whiling away your time and it's hopeless. And one famous problem is called the halting problem. And it is whether or not a Turing machine, this is the typical way you say this, whether or not a Turing machine accepts a string or goes into an infinite, I guess the way I should say this is, given a Turing machine M and string W, does Turing machine M halt on string W? Does it accept string W? That problem itself is not solvable because the Turing machine can go into an infinite loop and you'll never get an answer. So that's a really famous problem, by the way. It's called the halting problem. And it's the same thing as asking, is it possible to write a Java program or a C++ program that when given another program can tell whether or not that other program goes into an infinite loop? You'd think maybe that'd be possible, right? Well, it's not. Not in general. You might do it on small examples, you might do it on limited examples, but in general, that problem's not solvable. An infinite loop detector, not possible. Unless you set certain restrictions, and then it is. But all that is for the advanced theory class. We are finished with this video lesson.